Okay, fundamental theorem. We have been working with part 1, or part A, of the fundamental theorem. So part A said that the integral from little a to little b of little f of x dx became capital F of x plus c from little a to little b, which that became capital F of b minus capital F of a. So that's what we've been working with for about the last week or so. So now we need to do the second part of the fundamental theorem of calculus. The second part deals with bounds u and v of f of x dx. The difference is that the first one in lowercase a and b, those are numbers. Okay, those are actual specific bounds. We call that a definite integral. U and v don't have to be numbers. Okay, u and v could be variables or functions themselves. Okay, so it could just be x, but it could be x squared, or it could be the sine of x, or it could be a combination of those two things. So what do you do when you have a function where the bounds are themselves variables? Right? When you have that, you want to take the derivative, because you want to get rid of that integral that has those bounds there. And so what we do is we show out front that we are going to take the derivative of this whole thing. So when you have an integral that has bounds where at least one, if not maybe both, of them are not a constant, then you're going to want to take the derivative. The result of that is this. You still have lowercase f, because you haven't done an antiderivative. All you've done is get rid of the integral. Right? Taking the derivative, all you've done is get rid of the integral. You have lowercase f. But you have to plug in the bounds. So v would get plugged in first into regular f minus, times, because we're taking the chain rule, and v is a function in and of itself, you have to apply the chain rule to v prime. Then minus f with u plugged in, and then applied by u prime. Okay, that is the other part of the fundamental theorem of calculus. So we're just going to practice this over and over. All you've done really is knock out the integral. The integral is gone, and the bounds are substituted in. The biggest thing that people forget here is the chain rule. Just like when you're taking regular derivatives, is that they forget the chain rule. Okay, so let's actually do this to some real problems. All right, suppose you are given y equals the integral starting at 2 but ending at 2x cubed of the function sine of t dt.
What is the,
What do you need?
oh, I thought before you clarified the parentheses, I thought it was like absolute value.
Oh, yeah, sorry. Yeah, and parentheses. Okay, so we want to get rid of that integral because the upper bound of the integral is not a definite number, okay, not a defined number. It's an expression of 2x squared. So what we're going to do is take the derivative. So y prime, that will get rid of the integral, but does not get rid of sine. And then the sine is substituting in the upper bound, which is 2x squared, cubed, times the chain rule of that upper bound. No, just of the upper bound. Okay, so 6x cubed squared minus sine of 2 times the chain rule of the derivative of 2, which is 0. So we are left with y prime to be 6x squared, which is typically written in front of the sine of 2x cubed. We'll see what the purpose of this is later, but right now we're just practicing getting rid of the integral. Okay, we need to get rid of the integral. The purpose of getting rid of the integral is because we can't work with an integral that doesn't have specific bounds.
How do you visualize?
We're going to talk about what it means in a minute. Yep.
So if you actually try and solve for y there, would you then take the integral of that, of y prime?
Yes, which we will learn how to do.
Right now?
No, but yes. So now if we actually wanted to solve for what y equals, we would have to learn how to do the but that's a product now, right? And we don't yet know anything about the product rule for antiderivatives. We haven't learned that yet. So, but we're learning this step first, okay? All right, let's try another example. That's a really good question. Okay, how about y equals the antiderivative from a to 2a of the quantity 1 over 1 plus t squared dt. Because and again, if we had normal bounds, if we had bounds like 1 to 7, then go ahead and do it the other way and actually do the literal antiderivative. Okay, but we don't. We've got, in this case, both of our bounds are undefined. They're an expression rather than being a constant. And so then we want to get rid of that integral. So y prime, let's write it as Leibniz would do. Leibniz would say dy, and I'm curious to know what you think the lower part of that is going to be.
A.
Okay, well, it's either t or a. Okay, in this next step, what will I be substituting in? The a things. And so the t won't be a part of our problem anymore. And so it is a. Okay. All right, so we just keep our function 1 over 1 plus something squared. And what goes into that is quantity 2a squared. And then this is the place most people forget, is that you're required to do the chain rule on the expression 2a, which is going to be 2, minus 1 over 1 plus the expression of just a squared, and then times that chain rule, which is just 1. And so I end up with a simplified dy dA is 1 over 1 plus 4a squared minus 1 over 1 plus
2 over 1 plus 4 squared.
yes, times 2.
So we leave it there.
Leave it like that. Yep. Okay. Let's try another one. All right, find a tangent line to y equals the integral of 2x to 5 of 1 over t dt at x equals 1. What two things do you always need to write a tangent line?
Slope
You need the slope
and then given point.
and you need a point. All right, you need a slope and a point. So to find our point,
Plug that in.
we plug x equals 1 into y. To find our slope, we're going to have to plug x equals 1 into what? Y prime. So to find our point, we will simply plug in 1 into the function that we have. To find our slope, we're going to have to convert it to y prime first and then plug it in. All right, so let's find our point. Our point is simply plugging in 1 into what we have, but where?
1 over t.
No. Into the x position, not into the t position, it is an x value. So we are going to plug it into the x position, so it would be 2 times 1, 5, 1 over t dt. Now we have actual real bounds. Our bounds are 2 to 5. So we're going to do this problem just like normal, like we have. So what's the antiderivative? We're actually going to do an antiderivative. What's the antiderivative?
Natural.
ln of the absolute value plus c from 2 to 5, which is going to be ln 5 minus ln 2, which is going to be ln of the fraction 5 over 2. That is my point. 1 comma the natural log of, okay, so my point is x is 1, the y value is the natural log of 5 over 2. To find my slope, I need a y prime to work with. How do I get a y prime to work with? I use the second part of the fundamental theorem. So to get my slope, I need to look back at what I had for y, which was this. I need to find the y prime first, which means getting rid of the integral. Okay, so I'm going to rewrite it right here so we have it to work with. 2x 5 1 over t dt. Y prime means getting rid of that integral. Okay, so if I get rid of the integral, I'm going to put a double line through that to show I'm getting rid of it. What I'm keeping is the 1 over, and I'm substituting in what number? 5, and I'm multiplying by the chain rule,
0.
which is 0, minus 1 over, and I'm 1 over what number or what value? 2x, and I'm multiplying by the chain rule of 2. So overall, y prime came out to be equal to negative 1 over x. And I'm now plugging the number 1 into that to find my slope. So the slope will be negative 1. So now I have a point and a slope to work with, and I can write my tangent line. And this just goes back to, have we even done this since Christmas vacation? Okay, writing a tangent line, y minus y1 m x minus x1, and that's my tangent line. You don't have to simplify that. If you want to, you can distribute the negative 1. You do not have to, though. That's not part of the requirement. If you want to, if it makes you feel better, to have negative 1x plus 1 plus the natural log of 5 over 2 as your, that would be fine. Doesn't matter, but you don't have to. Okay. All right, let's try one more example, then I'm going to go back to the sheet with you. All right, find f of x if the integral from 5 to 2x of f of x, f of t, dt, is equal to x squared plus sine 2x. Okay, find f of x. Well, where's f right now? What is it coming after? It's right after the integral sign, right? Do you see where f is? Okay, I see where f is, but that's f of t, and I need f of x. That's okay, that's f. Okay, that's where f is at least. So what do I have to get rid of? I have to get rid of the integral, so I'm going to put a double line through it just to remind me I have to get rid of it. Okay, to get rid of that integral, what do I keep? Well, I keep f. Oh, I made a mistake. I apologize. There's no 2 there in my upper bound. You can erase that. Okay, here we go. I keep the f, and I plug in the upper bound. Right? And what is the upper bound? X. And the chain rule on that is 1 minus f of, now I'm using my lower bound, 5 times my chain rule of 0. Okay, I just did the derivative on that side. But in math, if you do the derivative to one side, what do you have to do to the other side? Also take the derivative. So keep taking the derivative of the other side. And what's the derivative of x squared? 2x. What's the derivative of sine 2x?
Cosine 2x times 2.
Cos 2x times the chain rule again, so there will be a 2 in front of it. Okay, have we found f of x yet?
Yes, we did.
Okay, so we've got f of x times 1, that's f of x. We have f of 5 times 0, which is 0, so f of x equals 2x plus 2 cos 2x. All right.